Hi everyone, this is Mrs. Terigno, and this is the second lesson in our Euclidean geometry unit that talks about just a couple of odds and ends, a couple of words that we really need to focus on a little bit. But again, a lot of this is stuff that we already covered in our little vocabulary unit. So I'm going to move kind of quickly here. There may be some definitions that you need to, that are blank in your notes and that you need to copy in. I probably won't pause for enough time here in the video for you to copy those down, just because I don't want you to be sitting and listening to dead space, and also because you should already have them written down in your vocab packet. But at any point, if you need to pause the video to finish copying something down, please do. Okay, so Euclidean geometry, which is what we've been talking about, and all of the geometry we're doing this year is considered to be Euclidean geometry, is built on a set of postulates, which are really a set of assumptions that are going to sound a lot like common sense, but we sort of need to lay those down as our ground rules before we can do any sort of building on that. So the first one of these big postulates is called the distance postulate, and it has a couple of different parts. First, the uniqueness property, and the uniqueness property says that there is a unique distance between 2 points, meaning if I draw 2 points, so a point here and a point here, there's only one way to measure the distance between those 2 points, and it would be on a straight path, that there is only one possible distance you could get here, okay? And that sort of eliminates the possibility of saying, like, well, why couldn't we just measure like this? Because that's not the straight path, and so the way we define distance, we define it as having to be a straight line. So uniqueness property says that when I have 2 points on a line, no matter how I measure it, it's got to come out the same. The distance properties says that to find the distance between the way to find the distance between 2 points is to subtract their coordinates. And one of the properties that we talked about on Friday with Euclidean geometry is that I can turn any line into a number line. So I can take this line and say, okay, I'm going to call this point 0 and I'm going to call this point 7, and then I could technically number all these points in between. And so then to find the distance between them, I would find the difference in the coordinates. And remember, difference means subtract. Now, that explanation is a little bit oversimplified, because technically, if I do 7 minus 0, I get a distance of 7. But if I do 0 minus 7, I get a distance of negative 7, and that's a problem. Have you ever heard anyone say, get in your car and drive negative 7 miles? No, because you can't have a negative distance, okay? So when I'm asking you to measure distance, it's counting the number of units. It's not saying positive or negative. So distance always needs to be positive, and we can accomplish that by saying it's the absolute value. I don't know how much you've done with absolute value before, but absolute value basically says we're only worried about how far away the number is. We're not worried about what direction it's going in. So absolute value is always positive, and that's kind of how we deal with that. So we would say, go ahead and subtract the numbers any way you want, but just make the answer positive. The additive property, and there's a picture on your notes that'll hopefully help you with this, that if point B is on segment AC, then AB plus BC, and remember these are talking distances. Remember when we talked about those symbols? The distance from A to B plus the distance from B to C has to equal the distance from A to C. And again, I think the easiest way to think about that is to look at this picture. Okay? This is saying that if I know this distance is X and I know this distance is Y, that I can just add those two distances together to get this whole distance. And again, that is common sense. Hopefully that's common sense. You look at that and say, of course, if this was 3 and this was 2, then I could say, all right, 3 plus 2 is 5, and that the whole length would be 5. But that's just one of those things we have to lay out as one of our ground rules. This page I'm not going to say a ton about because we covered all of this back in our vocabulary section. I just want to remind you the difference between all of these symbols so that you understand them when I write them down. Remember that when I draw the little line over with no arrows, that's talking about a segment, meaning that it's a piece of a line with two endpoints. If I throw the arrows in there, I'm talking about the entire line that extends into infinity. A ray is an arrow pointing in one direction, so it starts on one point and goes forever in the opposite direction. And just remember that when you label a ray, that the first letter is always your endpoint letter. And then this is the big one, that distance is when you just put the two letters together. So this is always a number, okay? That represents a number. So if I were to say, if I were to write AC, just like that, what that is really saying is what is the distance from A to C? And remember a minute ago we talked about how you can find distance by subtracting. So 5 minus 1 is 4. So I could say AC equals 4. So see, this notation is always equivalent to a number because it's equivalent to a distance. And it's also always equivalent to a positive number. Okay, so let's talk about what the word between means. If I have this point and this point, and I wanted to draw a point that was in between, we really need to be careful about how we define that, because would this point be considered in between? Would this point be considered in between? Okay, so we need to think about that. The geometric definition of between says that point X is between point A and point B if and only if, and we're going to talk about that wording later on, X lies on segment AB. So let's draw what this is talking about. Let's say, oh, I can't get rid of those. Let's say this is point A and this is point B. And it says point X is between A and B if and only if X lies on segment AB. So this would be segment AB. Point X has to be somewhere on this segment to be considered to be in between. So it could be there, it could be there. Any points in here are considered to be between A and B. But a point up here or down here is not between. Okay, so remember, between means it lies right on the segment between the 2 points. Another sort of related definition is opposite rays. So we've talked about what rays are. They're just single arrows. So XA and XB are opposite rays if and only if X is between A and B. That's sort of a meaningless definition, but let's draw that out. So here is ray XA. So here's X, here's A. Now if I were to draw XB up like this, okay, so here is ray XA starting at X and heading for A. Here is ray XB. But could we say this point X is between A and B? No, we can't, because based on our definition from up here, it's only between if it lies somewhere on the segment that's in between those 2 points. So right now, X is not between. Let me see if I can fix that. I didn't quite mean to get rid of all of that, but so for X to be on segment AB, that means A and B are here and here. Here's my segment AB. So point X needs to be in here somewhere. And then these also need to be rays. So right now I've only drawn segments. If I want ray XB, that would go out like this. If I want ray XA, that would go out like this. So I need to put arrowheads on the end of these. Hey, look at that. It makes a straight line. Opposite rays always form, and I don't even need to write the word straight, because in geometry all lines are straight. Okay? Opposite rays always form a line, because one arrow goes one way, one arrow goes the other way, and X has to be on the segment between the 2 endpoints, so it has to be in a straight line. So let's talk about how we define things in geometry. And we just came out of a vocabulary unit, so obviously you know the importance of having a good definition. Okay? So the things that a good definition, to to tell you, to explain to you what a word is, I need to include words that are commonly understood, meaning words that I can assume you already know, or previously defined. So that means words that maybe you wouldn't know just coming in off the streets, but we've already talked about together in class. So if I tried to explain to you what a bisector was by talking about lines of symmetry, well, you might know what a line of symmetry is, but you might not, and I haven't taught it to you yet, so I'm not allowed to use that word in my definition. It also needs to be accurate, which is sort of a given, but you've got to be able to say, yes, that's actually what that is. If I tried to write a definition of a triangle, and I said a triangle is a four-sided figure, that's not accurate. Okay, so it's got to be an accurate description. And you don't want it to include a bunch of unnecessary stuff. Sometimes there are things that are true about a figure or true about an object that you don't necessarily need to be part of the definition. Okay? So if I was going to define, let me think. If I was going to define what lamp was, okay, if I was going to define the word lamp, you know, I could say it's an electronic device with a light bulb that provides light. If I were to also throw in there, and they come in floor lamps, and they come in, you know, desk lamps, and Mrs. Torigno has a green lamp in her room, if I threw in all that other information, it really muddles up your definition. So you want to make sure that you're not repeating yourself, that you're not including anything that's unnecessary. So take a look at the definition of midpoint, and we've already talked about the definition of midpoint. It's the point M on the segment where the distance from A to M is the same as the distance from M to B. And again, this word, hopefully you know that it's going to be somewhere right in the middle. So remember, these little marks mean that these pieces are congruent, so the point right here where this distance and this distance are equal to each other. So this is a pretty good definition of midpoint up here. It's a pretty mathy one. We had said earlier it's the point in the middle, but that's a little bit too close to the actual word midpoint. It's sort of using the word in its own definition, and that's a no-no too. Let's look at these definitions down here and talk about why they might not be good definitions. So, for example, the midpoint of a segment is a point between the endpoints. Well, that's true. The midpoint is between the endpoints. But technically, based on what we just talked about, if this is an endpoint and this is an endpoint, isn't this point between them? But it's not necessarily a midpoint because this piece and this piece are not equal to each other.
Do you have any extra?
So this definition is considered to be inaccurate because it doesn't actually explain to me what a midpoint is. Okay, because it doesn't include the part about it having to be the same distance from the endpoints. Okay, let's look at the next one. The midpoint M of AB is the point M on AB between A and B, the same distance from A and B, so that MA is equal to MB. Whew, that's a lot of stuff. Okay, so first of all, I want to point something out. This says point M has to be on segment AB, and then it says it has to be between A and B. Well, doesn't between include the point having to be on the segment? When we said what between meant, we meant that, when we defined between a couple of slides back, we said that for a point to be between 2 points, it needs to be on that segment. So this is redundant. It's like I'm saying the same thing twice. And then here, I'm saying it's got to be the same distance from A and B. And then here I'm saying the distance from A to M has to be the same as the distance from M to B. Well, isn't that the same thing? Aren't I saying that the distance has to be the same and the distance has to be the same? So again, it's redundant. So this includes, I'm going to put the word redundant. Which is sort of a way of saying it includes too much information. There's too much stuff there. Okay? The midpoint of a segment is a point that is the same distance from each of the endpoints. Be careful here because some of you might be looking at that and going, I think that's pretty accurate. But look at this. If this is point A and this is point B, I could draw a point up here where this and this were equal to each other. So that point M is the same distance from A and B. Okay? So again, that is inaccurate. And the last one. The midpoint M of segment AB is the intersection of AB and a bisector of AB. Well, technically that is true. That's a perfectly fine definition. The problem is, at this point in the game, and I know we have talked about it because we did our whole vocabulary thing out front, but this early in the year, is bisector a commonly understood term? Would you know what bisector was if you were just trying to figure out what a midpoint was? Not necessarily. So this is not commonly defined words. Okay, so those are some of the issues we run into with definitions. Okay, so just some food for thought there. Okay, polygons. We've also already talked about polygons. So I'm not going to spend a lot of time talking about the definition. I do want to point out, when we wrote down the definition, there were 3 main properties of polygons that are important. Polygon has to be closed, okay? The sides have to be line segments, which is a fancy way of sneaking in the requirement that the sides have to be straight, no curves. Sorry, my handwriting's really bad there. And they have to intersect only at the vertices, meaning you can't have lines like crossing in the middle. So let's look at these shapes. This one here, does it fit all 3 of these? It does, so this one is indeed a polygon. What about this one, this oval? Nope, this one is not a polygon because the sides are not straight. This one here, not a polygon because the sides intersect somewhere other than their endpoints. What about this one? This one is a polygon. It's a concave polygon, but the sides are straight, it's closed, and there's no crisscrossing in the middle, so it's fine. This one down here, not a polygon because the corners are curved. Okay, so again, because the sides aren't straight, this one was a polygon. This one here, sides are all straight, it's closed, sides intersect only at the vertices. That one is a polygon, so is this one. And this one down here, not a polygon because it's open. It's not a closed figure. Okay, gosh, that got really messy. I apologize for that. Concave and convex, we've also spent a long time talking about that. So, again, just a real quick refresher. If a shape is convex, that means anytime I pick 2 points on the shape, it doesn't have to be at the corners, and I draw a segment, that segment stays entirely within the figure. Okay, there's no way I could draw a line outside the figure. Even something like this, if I pick a point in here, whoops, didn't mean to, a little off there. If I pick a point up here and down there and connect them, that segment stays within the figure. Whereas if I go down here to the non-convex ones, I can draw in segments here. I could draw in a segment here, and here, and here. And all of those green segments are connecting points on the figure, but it goes outside of the figure. That's the big difference between concave and convex. So let's talk about circles for a minute. And I know we have talked about circles quite a bit, but one of the things I mentioned when we were talking about circles is probably all of you could draw a circle. Could you write a definition for a circle? Now hopefully you could. Definition of circle, in case you don't remember, set of all the points in a plane that are the same distance from a given point. Now if you know anything about circles, you know that circles have some pieces, and one of their pieces is the radius. The radius is that same distance. So whatever that distance is all the way around, that's equivalent to the radius of the circle. That given point in the middle is the center of the circle. So that's what we would call the center. Just a picture for you for reference in case you don't know what a circle is. Just kidding. There's your center there. And then any of these lines I draw would be that same distance apart. That would be your radius. Okay? So is a circle convex? Well, if I pick a point on the circle and another point on the circle, is there any way to connect them so that it goes outside the shape? Nope. So yes, it is convex. Is it a polygon? No, because the sides are not straight. Oh, I realized I had those popping up on their own. Okay? Okay, so some practice for you here. Which of these are polygons? Well, letter A has an issue going on here, okay, because the sides don't, or the sides cross in the middle, so this is a no. Here we've got some sides crossing, so this is also a no. What about this one? Letter C? Yeah, that one has no issues. That one's a polygon. And down here, convex or non-convex? Well, again, if I pick a point here, connect them, they stay inside. I don't see any way I could draw a line that goes outside, so this is convex. With letter B, if I pick a point here and connect them, that goes outside, so this is non-convex. Here, point, connect, stays inside, so does that one, so does that one. This one's convex. What about a line? If I pick 2 points on the line and connect them, does it always stay on the line? Yep, it sure does, so that's convex. Okay, I'm not going to attempt to do the drawings because writing with a stylus, I'm never going to be able to make it look halfway decent, but I'm very confident that you would be able to do this by this point. So if you have finished up to this point, just make sure your notes packet is filled in. You'll get some points for that when you come in on Monday, and then on Monday you'll have an assignment that covers the previous lesson and this one, and you'll have some time to work on it in class. Thanks for your time.